Hello, Alexander. Can you hear us?
Yes, I can hear you. Can you hear me?
Very much, very much. Yeah, thank you. Thank you.
Very good.
Very
All
sorry
right.
to be here. Yeah. Okay,
So
I'll
let me know when I should start.
I'll just let Mr. Vivek Borkar take over.
Yeah. Okay.
Okay, so the next speaker of this session is Professor Alexandre Proutier. He's a very well-known person in stochastic networks, particularly communication networks. And for past several years, he has been contributing a lot also to bandit literature. So today we will talk about low rank, oh, it's a third topic this time, low rank reinforcement learning. Alexandre, go ahead.
Yeah. Okay. Thank you very much. Can you all hear me very well? Yes. Yeah.
Yeah, we can hear you.
Okay. Very good. So thank you very much for the invitation, and really sorry not being with you. Now I have my passport, and I I hope I get another invitation later on. So I will be talking about low-rank reinforcement learning. This is joint work with Yassir Jedra, who was my PhD student, who is now a postdoc at MIT, and Stefan Stojanovic, who is also my PhD student. Um, so the talk is based on two papers that we published last year and this year. And if you are interested, I send the slides, so all the references will be available. All right, so the talk is about reinforcement learning. In reinforcement learning, typically we model the problem as a controlled Markov chain defined by gamma, a discount factor, a state space S, an action space A. Here, stationary transition probabilities. So it means that P of S prime given S and A is just the probability to move to state S prime, given that you are currently in state S and that you choose select action A. And the final component of the Markov decision process is a reward function that will be here assumed to be just a function of the current state and the selected action. So as you all know, I mean, there is the notion of value function introduced by Bellman that allows us to actually derive what's the optimal policy for this Markov chain optimal control problem. The goal, of course, is to maximize the expected cumulative reward with discounts. And the value function V star of S is by definition the maximum expected reward you can gather if you start from a given state S. And it satisfies this Bellman's equation, which is essentially telling you what are the optimal policy as well. So the goal of reinforcement learning is to kind of solve these Bellman's equations without actually having access to the reward function or the transition probabilities. So you want to learn an approximately optimal policy by just observing trajectories of the Markov decision process. So there are two paradigms in reinforcement learning. One is called model-based, the other one is called model-free. In model-based RL, typically you would learn a model of the system dynamics, assuming, for example, that you know what the reward function is. And from this model P, you would deduce the value function, which in turn would give you an idea of the optimal policy. So there is a very natural result that is called a value difference lemma that connects the estimation error that you do for the value function compared to the estimation error of your model. So this value difference lemma tells you that entry-wise, V star minus the estimated value function in a given state would be bounded away by some kind of error you make by estimating the matrix PA, PA being the transition matrix of a Markov chain where essentially you always choose the action A. What is important to note here is that in the value difference lemma, the norm, the error on the the estimation of the transition probabilities are in the 1 to infinity norm. So it's a norm that is essentially the max over all possible rows of this matrix of the total variation of the corresponding distribution over states. Okay, so this is a norm that is a bit better or a bit more precise than the spectral norm on the Frobenius norm when it comes to matrices. So that's one thing, one key aspect here is that if you want to have a guarantee in model-based RL, you need to estimate the transition probabilities in a kind of 1 to infinity norm. The second paradigm for RL is model-free, and essentially this is typically this is the classical setting where you learn the value function directly, and for this you need to you want to have guarantees in the infinity norm. So it means that you want to have entry-wise guarantee for the value function for all S. Okay, please feel free to interrupt me in the chat. I have the chat window open.
Alexander, will you be able to comment on which one of these two is better than the other, or is model free always better?
No, model-based is always better. Samples, it depends what you are asking for. Yeah, it's very difficult to say. Model-based, typically what is nice is that you can incorporate very easily side information or structural information you have on the dynamics a priori. And in turn, if you do that, typically you would have a lower sample complexity. Model-free is kind of very appropriate when you don't know much about the system and where you, I mean, there are different scenarios. We cannot say that one is better than the other. So in RL, there are kind of a lot, there are different kinds of problems that people want to solve. There are gigantic problems or combinatorial optimization problems where essentially, even if you have the model, you don't know how to compute the value function. And this is the example that you see in the news for RL, like AlphaGo or these kind of things. We know exactly how the game is played, but we cannot essentially computationally we cannot compute V star. And essentially RL is there to essentially approximate or learn the solution of a combinatorial optimization problem that is huge. When the other side of RL is when you have small models, low dimensions, and where the problem is not combinatorial, but it's more like a statistical problem of learning the dynamics. So RL is covering a huge spectrum of practical problem, and it's very difficult to say if one is better than the others. You can resort to kind of lower bounds in terms of sample complexity, and then at that time, typically the two approaches becomes kind of equivalent. But again, I mean, it's kind of a difficult question to answer.
Yeah, I thought if you have a massive model, learning the probabilities will be very demanding, right? RL will just focus on the important areas and figure out important things quickly. But that's not the case, you're saying?
That is true. That is true. Yeah. Yeah, but but again, I mean, with model free, you struggle incorporating some additional side information that you could have on the model. So, for example, there are a few recent examples. So essentially, the state-of-the-art algorithm in RL are kind of Dreamer for model-based, and for model-free, this kind of alpha zero kind of things, and Dreamer is performing better because I don't know. I mean, it's because essentially you can learn the model and then you can simulate. You can do a lot of more stuff when you have a model than when you don't have a model. So it's again, it's not so easy to answer this question. I don't know.
Well, that's very good. Thanks. Yeah, I thought, I didn't know that there was so much
All
confusion.
right. So yeah, speaking of lower bounds, if you want to learn an optimal epsilon optimal policy, we know that anyway it will require a number of samples, even in the generative model where you can gather an experience. An experience is a state, an action, a reward, and the next state. Even if you can gather experiences using a generative model, so it means that at every experience that you gather, you can go to another state and gather an experience from there, so you don't have to follow a trajectory. So even if you have a generative model, then the sample complexity to find an epsilon optimal policy is scaling as S times A divided by epsilon square times 1 minus gamma cube. So 1 over 1 minus gamma can be interpreted as the time horizon. So it's time horizon cube times the number of states times the number of actions divided by epsilon square. And when you think about it, so this is a minimax lower bound, and you understand that the product SA is telling you that, well, you have to learn kind of the dynamics in every state action pair. And so that's why you actually need this kind of sample complexity. So this minimax lower bound is, of course, valid for any kinds of algorithm, including reward model-based or model-free. If you have a large state space or large action space or both, then you need you are going to struggle to learn an epsilon optimal policy. So typically what you want to introduce is some kind of assumptions about the structure of the system. So you can do assumption with respect to the structure in the model-based setting, where essentially you will say that the dynamics have some structure. Or you can do it in model free, where you would assume that some functional of interest, like the Q function, would have some structure as well. So in this talk, I will focus on what we call the low rank structure, which for the model-based is saying that the dynamics is represented by low rank matrices. So for example, the probability, the transition matrix of the Markov chain corresponding to always selecting the same action would be of rank D, much smaller than S. And in the model free setting, it could well be that the Q function is seen as a matrix of with S line and A columns would be of low rank. So D would be much smaller than the minimum between S and A. The first assumption for the model-based is essentially motivated by what's called block MDPs. So it's a scenario where essentially you have the agent as a huge state space, observe a state that has a very high dimension, but a lot of these dimensions are kind of redundant or not informative. And there is an underlying latent state of much smaller dimension that actually is driving the dynamics. Okay, so this is called block MDP. The second model free, the low rank assumption on the Q function is motivated by the fact that if you have a continuous state space, an action space, then actually naturally, if Q is a smooth function, then you have some kind of low rankness that becomes natural. And to do that, to see that, I mean, there is a very nice paper by Devravat Shah and colleagues a few years back to explain these connections. Yes, so that's what I wanted to say. All right, so I will do both. I will treat both cases, model-based and model-free. And I will start by assuming that the transition matrices are low rank. So this is the low rank, model-based low rank RL. Okay, so here I will focus on a single Markov chain. So, and my goal is to essentially estimate the transition probabilities and assuming that this matrix is of low rank or approximately low rank. So n is the size of the matrix. So n is equal to S here, the number of states, if you want. And we want to have a matrix that is of rank D, much smaller than n. So the problem that we want to solve is to estimate the low-rank transition matrix P from a single trajectory of the Markov chain. And remember that we need to have guarantees with respect to the norm 1 to infinity so that it can translate to a guarantee for the estimated value function. Even better if we can have entry-wise guarantee for this matrix. Okay, so the assumptions that we make is that, well, we have irreducible Markov chain with some stationary distribution nu, and we will control the heterogeneity and incoherence of the matrix M, that is essentially multiplying every line of P by the stationary distribution. And by controlling the heterogeneity and incoherence of the matrix, I mean that we will have results that depends on the condition number of this matrix M and on the definition of the incoherence of this matrix. Essentially, when studying low-rank matrices, you understand that, for example, if you have one entry that is non-zero and all other entries that are zero, this matrix is of rank 1, but it's very difficult to estimate if you don't observe this entry. If you are not lucky, maybe you don't observe it. So you need some kind of assumptions to be able to kind of recover the matrix from observing a few entries. So the data that we want to start with is a trajectory of length t of the Markov chain. Okay. So first of all, of course, we can connect the transition probability matrix P and the matrix M, because M is just obtained by multiplying each line of P by the stationary distribution of the corresponding states. So P is just a normalized version of the lines of M. Okay. And if you have an estimator of M, then you can build kind of easily an estimator of P by renormalizing your estimator. Okay. So when it comes to recovering the matrix P or M, we will look at we will try to recover the singular subspace of the matrix U. And when it comes to the norms that we use to look at what's the performance of our estimator, we look at the 2 to infinity norm of the recovered subspace. Of course, the recovered subspace is defined up to rotation. So that's why we have the minimum over all rotation O in this performance matrix here. When it comes to matrix estimation, as I told you, we need the 1 to infinity norm or even the entry-wise guarantees. So when you look at this problem, you face two unusual challenges in matrix completion or matrix estimation. First of all, you have correlated observation because you are observing a trajectory of a Markov chain. So the entries, for example, if you count the number of times you have a transition from one state to another, this entry will be correlated with the other entries because you are following a trajectory of a dynamical system. So depending on whether you went through certain state, maybe some other state would be visited more often. Okay. So you have correlation between the observation, between the empirical estimate of each entry of the matrix. The second challenge is, of course, if we want entry-wise guarantees, then the usual techniques to give guarantees are not applicable. So we have a very natural way to handle correlations. The algorithmic solution is, of course, to split the data into tau subsets of transitions, where you separate the transition from a tau step. Okay, so you construct matrices that are corresponding to, let's say, the Markov chain is every tau step. Okay. And by doing that, you hope that you kill the correlation enough so that the estimated entries can be seen as almost independent. After you do that, after you split your trajectory into T over tau matrices, you estimate these matrices independently. You take their rank R approximation, and then you reconstruct your full estimator by just summing or averaging your obtained estimator. If you want to analyze this algorithmic solution, you will need to do a few kind of approximation. What we do is a multinomial approximation of the empirical matrix, and then a Poisson approximation of the observed entries. For the entry-wise guarantees, essentially it's more like an analytical tools, because we are applying spectral method. As you see, we just do SVD. So to analyze the performance of spectral methods when you target entry-wise guarantees, you need to essentially apply an argument that is called the leave one out argument, that was introduced by Emmanuel Abbé and co-authors a few years back. And this is an example of our result that we have in the paper. And the slide is called optimality of spectral method, because we can prove that the guarantees that we have here are kind of minimax optimal. So if I read a little bit the theorem here, we assume that the matrix M is homogeneous in the sense that the condition number is not scaling with N. Also the incoherence of the matrix is controlled. The rank is also not scaling with M, but that's the N. Sorry, that was the initial assumption. And then we also assume that essentially the entries of the matrix are kind of comparable. Okay. So we show that essentially we get a lot of guarantees for the subspace recovery of the algorithm. We get guarantees for the 2 to infinity norm of the estimator for the matrix M. For the entry-wise guarantee, we have entry-wise guarantees, and we can also derive similar guarantees for p hat in the 1 to infinity norm and the entry-wise guarantee. So in entry-wise guarantee, you see, for example, that we get log nt over square root of nt as a guarantee, where t is the length of the trajectory and n is the number of states here. Okay, so if you think about it, for an homogeneous frequency matrix or transition matrix, the 2 to infinity norm of the u, the singular vector, is scaling as 1 over square root of n. So this implies that, for example, the entry-wise, the L infinity norm, the infinity norm of P is scaling as 1 over n. And so for all these matrices, metrics, our estimate achieve a relative scaling error of at least square root of n over t. Okay, so that's, for example, here. You may think, oh, it looks too good to be true, because it's essentially the error is decreasing in n, the number of states, but actually you have to beware that the typical entry of P is scaling as 1 over n as well. So it doesn't mean that we have a better and better algorithm as n is growing. The relative error is indeed scaling as n square root of n over t, up to logarithmic factor. We have a good reason to believe that this is minimax optimal because there exist lower bounds, minimax lower bound for this kind of estimates. And this is a paper by Zhang and Wang in 2019. Here I gave just the result for homogeneous matrices, so where we control kappa, the condition number, the coherence of the matrix, and so on. But actually, we have result for any matrix, where essentially the dependence in kappa, mu, and so on is actually written explicitly in the upper bound or inner guarantees. Okay, so a sketch of the proof. As I told you, what we do is a series of approximation to kill the correlations in the data. We approximate the joint distribution of the number of transitions by multinomial distribution Z, and we have some kind of rough kind of comparison of the distribution of Z and the distribution of observation. The second approximation is a Poisson approximation. So it means that Z now is approximated by Y being a Poisson, a matrix with independent Poisson entries with averages that corresponds to those of the entries of Z. And again, we can actually relate the distribution of Y to that of Z in kind of a sufficient manner for our analysis. Finally, as I said, I mean, one of the core contribution is to apply the leave one out argument to get entry-wise guarantees for Poisson matrices. And I really don't have time to detail this, but this is kind of the core ingredients to the main ingredient to get the guarantees for the singular subspaces and the guarantees entry-wise of the matrices. Okay, so that's good. So we can essentially estimate the transition matrices and in a 1 to infinity with respect to the 1 to infinity norm. So does it bring any advantage when we do reinforcement learning? Okay. So here I take what we call the reward-free reinforcement learning. So it's a kind of reinforcement learning task that is kind of popular today, which consists in first observing trajectories of the system without observing any rewards, okay? And then after you gather data about that corresponds to trajectory of the system, then you are given a reward function. The reward function is revealed. And from your data and the reward function, then you can essentially estimate the best policy pi hat of R, a function of the reward function. So this reward-free setting is popular because it's very convenient when you think about multitask RL for robotics, for example. So when you apply the above methods of model-based, so meaning estimating the transition matrices and using the value difference lemma, we can show that the sample complexity to get an estimation error for the value function over all possible reward function smaller than epsilon is scaling as NA over epsilon square 1 minus gamma cube. So N is the number of state, A is the number of action, and so on, okay? And we actually know that this is minimax optimal from a result that we published earlier. And what is interesting is to notice that there are also lower bounds for the scenarios where we don't impose any structure. Without structure, this sample complexity would scale as n square A over epsilon square 1 minus gamma cube. So it means that by exploiting the lowering structure, we win a factor n when in terms of sample complexity, where n is the number of states. So that's a significant improvement, but you see that it's not really kind of enough because the sample complexity is still a scale as n times A. And this is something that you cannot beat anyway in this setting. Okay, is there any question on this first part? No? Okay. All right, so I will continue, and I will now turn my attention to model 3, low rank RL. In model 3, low rank RL, I will just try to estimate the Q function directly instead of learning the model, the dynamics, and then deducing the value function. So more precisely, I'm defining the state action value function Q pi of a policy pi, and I will assume that this Q pi seen as a matrix S times A matrix is of low rank D, okay? Okay. So the objective here is to learn pi hat such that, of course, it's epsilon optimal. And we want to do that from the data. There are some existing work on this kind of problem by Devravat and co-authors, as I mentioned earlier in this talk, and by Tyler et al. A bit later. In both this paper, they kind of the first paper by Shah et al. Assumes that the agent or the learner has access to what we call the anchor state, which are states that have a very specific role in the matrix Q pi. And in general, there is no real reason why we would have access to these states. The second paper by Tyler et al., they try to remove these assumptions and they try to randomly select these anchor states. But as a result, their method can only work if essentially they have guarantees in the sample complexity that scales as the incoherent square of the matrix. And this is kind of a bit limiting. So we will try to do better than these two papers. Okay, so the parameter alpha here that you see in the formula is called the matrix spikiness. It's kind of it's related to the ratio of the entry-wise norm of Q divided by its frobenius. So how spiky is the matrix? Okay, and the parameter mu, of course, is the incoherence or the coherence of the matrix as defined earlier during the talk. Okay, so it's very important to realize that spikiness is much more general than incoherence. So being spiky is less restrictive than incoherence. So it's, I mean, to realize that, we can see that there are matrix Q such that the spikiness is equal to 1. and the coherence is still scaling with the number of states, the dimension of the matrix. And if you are able to actually control the incoherence of the matrix, then you are also able to control the spikiness of this matrix. So being spiky is much less restrictive, and ideally we would like to have guarantees that are only a function of the spikiness and not the coherence of the matrix, while not knowing not having any side information or a priori information on the matrix. Okay. All right. So existing result on low rank matrix estimation. So typically, people look at the spectral norm or the Frobenius norm guarantees. And typically for this guarantees, the sample complexity to recover the matrix with some given precision is scaling polynomially in the incoherence of the matrix or polynomially in the spikiness of the matrix. And that's classical result in low rank matrix estimation. Now, when it comes to the guarantees that we are interested in, like 1 to infinity or entry-wise guarantees, there are much less work on this. And existing work, all the existing works, they have a scaling that depends on the coherence square of the matrix, the spikiness square of the matrix, and the condition number square of the matrix. So we try to essentially reduce this dependence and have better results. So our low rank estimation methods has actually 1 to infinity or infinity norm guarantee with a sample complexity that is scaling as alpha square kappa square. So we were able to actually remove any condition or any dependence in the coherence of the matrix. And this can be really significant when for some matrix, because again, mu square would scale as S. So by removing mu square, potentially you improve the sample complexity by a factor S or N, the dimension of the matrix. So it's very important. Okay, so if you have a way to estimate the matrix, the Q pi, then you can do a reinforcement learning algorithm that would just iterate in a policy iteration manner. And this is the algorithm that we call LoRa pi. So you repeat policy evaluation and then policy improvement steps. This is the classical thing in reinforcement learning. The first thing that you do is that you have your policy pi t at step t. Then from the data that you can gather from this policy, you would estimate the matrix, the corresponding matrix Q pi. So Q hat T is an estimation of the state action value function of the policy pi t. And from this estimation, you know that you will improve the policy by just taking the greedy action with respect to this matrix Q hat T. Okay, that's the classical policy iteration method. And if we plug our guarantees for the matrix low rank matrix estimation of Q pi, and we essentially run this algorithm, we show that with high probability and using less than t samples, you get an epsilon optimal policy, provided that the sample complexity is smaller or is scaling at most as alpha square d square s plus a divided by epsilon square 1 minus gamma 8. So when you remember the lower bound that we had earlier without structure, the lower bound was SA over epsilon square 1 minus gamma cube. So here we have replaced SA by S plus A. So the low rank is helping by reducing the complexity, the sample complexity. On the other hand, you are paying the price of the spikiness. For now, we are not able to kind of tell you interesting things about the dependence in terms of the time horizon. So here, we know that the horizon should come at the power 3, 1 over 1 minus gamma cubed, but we don't know how to do it. Okay, I have not a lot of time remaining, so let's try to. I will tell you a little bit how we do estimate the matrix Q pi. We estimate the matrix Q pi by introducing first the leverage scores of the matrix. So if you have a matrix Q and you do is it SVD U sigma V W transpose, we define the left and right leverage score L and rho of the matrix as some kind of L2 norm of rows of the corresponding matrix of the matrix stacking all the left and right singular vector of the matrix. Okay, so this is for L and this is for W. This is for U and this is for W. So our low rank matrix estimation has two phases. We use half of the budget to essentially generate trajectories. From there, we build a very simple estimator of the Q matrix. We do a universal thresholding, an SVD with universal thresholding to estimate the rank of the matrix and to estimate its right and left singular vectors. From this rough estimate, we will essentially deduce estimation of the leverage scores of the matrix. What is interesting is that if you find states that are of high leverage score, typically they would constitute what the other the other papers that I mentioned earlier are called anchor states. So this is our way of finding the anchor state, if you want. So that was the first phase. And then after that, we leverage the classical CUR decomposition of low-rank matrices. So if you see that if there exists a subset of lines and a subset of columns such that the restricted matrix is full rank, then you can recover the entire matrix by just looking at the line and rows corresponding to this set I and J. Okay. And so in the second phase of the low ranks matrix estimation, we just sample the anchor states. We sample a little bit more anchor states than needed. We sample D log D anchor states and anchor actions according to the corresponding estimates of their leverage scores. So, okay, so essentially in our set I and J, you will have most likely states and action with high leverage scores. And we use these leverage score to sample trajectories starting from this the corresponding state action pairs. Okay, and after we kind of estimate the submatrix Q in a much more precise way on the line I and the column J. And from this much more precise estimator, we can actually reconstruct entirely the matrix using the CUR decomposition. Okay, so we have, of course, an analysis of the low-rank matrix estimation for any policy. We show that we estimate the leverage score in a nice way. I mean, kind of after this number of samples, we can have this guarantee for the leverage scores. And we can have also a sample complexity for the entry-wise guarantee of Q. That is saying that, okay, the sample complexity should scale like this. So you see that you have a dependence in S plus A here. you have the dependence in alpha square, the condition number to the power 4, and that's about it actually. Okay, so this proposition 2 is the one leading to this theorem 3 when you iterate the process of learning the Q function of your current policy, your current estimated optimal policy. Okay, so I will conclude here. Just a few concluding remarks. So we try to solve low-rank RL problems here. And the main, essentially, ingredient for the analysis is a low-rank matrix estimation with entry-wise guarantees or 1 to infinity norm guarantees. And essentially, we show that spectral methods plus, meaning you need spectral method based spectral methods based algorithm are kind of minimax optimal. There are a lot of open problems for low rank Markov chain or MDP in general. The first one is what are low rank MDP really? So we are kind of working on this. It's a very interesting question, to be honest. There are, as you saw, dependence in the condition number of the matrix. So we try to remove this. And the last question that actually we solved recently is, can we make the method robust? So this is related to the first question, what are low rank MDP really? We actually believe that low rank doesn't exist really in low rank, but maybe approximately low rank, or some kind of definition of low rankness that is a bit less strict than the usual definition would actually make sense in practice. Okay, I will stop here and I will be happy to answer any questions.
Any questions?
So, Professor, I just wanted to ask, even
Yeah.
with to LLMs, there is the LoRa technique, low rank adaptation. So, is
Yeah.
there a relation between the two?
Yeah, there is probably a relation. I haven't really looked at what they are doing in low rank. Yeah, yeah, it's an interesting question. I think there is a connection, of course, but I cannot. I don't know what it is.
Because
It's
what I noticed was that technique in the LLM context came in 2022. And while your paper is cited like it was of 2020. So maybe they got inspired from reinforcement learning, LoRa techniques.
I don't think so. I think that I think these are people that are kind of not working on the same thing. So I would be very surprised if they were actually really inspired by the RL literature. I'm not so sure. Yeah, but yeah.
You.
Yeah.